the electron diffusion region.
Yes, thank you very much. So this is my first invited theory talk. Like normally I do experiments, and here you see my experiments. I'm not going to be talking about that today. But reconnection happens right in the Earth.
It's an honor to launch your theoretical career.
I'll see what I can do. You can tell me afterwards if I should go back doing experiment, right? So I don't really need to introduce much here. Like as you know, reconnection happens on the sun, in the Earth's tail, and also in our experiment. And like in particular, like I'm working together with some of my students, which are very theoretical minded, Ari Lee in particular, and also a new fantastic undergraduate student who's called Jonathan. And then Bill Dorton and Jim Drake has supplied me with lots of data over the years, and also Merritt Oisett and Bob Lin at Berkeley, and Jonathan as well. And Lijian Chen has supplied me with spacecraft data. So everything I do, I kind of try to root it in experimental observations. So this is an outline of my talk. Like, basically what I'm interested in is kinetic effects that has to do with electrons being trapped. And here you see a trapped electron in like a simple cusp geometry. The magnetic moment is conserved, and because there's a magnetic minimum at the center, it'll mirror back and forth like this. This is 2D, so the canonical angular momentum is conserved, and you see that this particle always bounces in the same field line. So it's very powerful. So in this particular case, it went to the left, it could have gone to the right. All right, so here's my actual outline. Based on this orbit motion, I'll try to build up a new model for the phase-space distribution function when we assume it's gyrotropic. So this is the function we parallel and we perp. And this only applies where the magnetic moment is conserved, so this only applies to guide field reconnection. And then based on this model, we can derive new equations of state that give you the parallel and perpendicular pressure as a function of n and b. So this basically amounts to a new fluid closure that could be applied maybe to study guide field reconnection in a fluid code, and maybe we can see the features that you actually observe in the PIC simulations. Then we'll try and see if we can apply these equations of state also to anti-parallel reconnection. And it turns out that it works really well, much better than I had anticipated. We can actually get scaling laws for this inner electron diffusion region. And finally, we also figured out the structure of the electron distribution inside these outflow jets. Then I want to get back to reality and compare to spacecraft observations. And it turns out with these new equations of state, you get parallel pressure that goes with n cubed divided by b squared. We find something similar to a CDL scaling. And with that scaling, you can support huge parallel electric fields. Like normally in plasma physics, we always learn that there's no parallel electric fields. But I find with these new equations of state, when they apply, you can actually have huge parallel electric fields. And I think we have evidence of that in the spacecraft observations. And that leads to the implication of all this for the generation of superthermal electrons. Okay, so first let's look at this new model. This work started with some spacecraft observation by wind out at 60 Earth radii, and wind went straight through this little diffusion region. I think it's been going out there for years, and there's like 8 minutes of data. That's really interesting. So right here at 8 o'clock on this particular day, wind was very close to the X line. And like these spacecraft can do something we could never do in the lab. They can measure the phase-space distribution function as a function of, so here you have f for a number of different energies as a function of the pitch angle. So 0 is along the field, 90 degrees is perpendicular, and 180 degrees is anti-parallel. So what you see is a very strong dip at 90 degrees. So there's very little pressure perpendicular to the field, and hence pressure along the field lines. This is a log scale. There's almost a factor of 10 decrease in f when you look perpendicular to the field line. If you go into this maybe more familiar way of representing the distribution function in the parallel perp space, then these dips correspond to the flattening of the distribution function. Like so, if I take the 2 kilovolt curve here, like if you follow this dashed line, that's 2 kilovolts, and this variation in f along this curve corresponds to the variation you see here as you go along. Had it been a Maxwellian, right, it would just have been constant. Okay, so I'm going to present a very simple model that I think can explain this. So we want to figure out what is the distribution function inside this region close to the x-line. So I'm considering this flux tube now. And so I'm going to ask myself, if I feed this region with a particle with almost 0 parallel velocity, but some perp velocity, and I'll let it go in here, then where will it end up in V parallel V perp space when I reach this point? So now for this particle, I assume the magnetic moment is conserved. To begin with, I only have magnetic forces, so also the energy is conserved. And yeah, the magnetic field is less in here, so it's clear that V perp has to be less, yet the energy has to be conserved, so it has to pick up some parallel velocity. So this is where it's going to end up. Okay. So what will happen to this if I feed in half a Maxwellian up here? It will simply just be squeezed down to this area by using Liouville's theorem or Lazo equation. So if you feed in half a Maxwellian, you only have magnetic forces, you squeeze that down to like a smaller pi, and again, because the energy is conserved, down here it stays a Maxwellian. You can do the same thing from the other side, and you get another pi there. Right, so now we have a gap here, and we have to fill that with something. And what that's filled with is those trapped particles that I had in my outline. So you should imagine this flux tube has been convecting in and has been filled up with trapped particles earlier on that accumulate. And they basically fill up this region here. And it's quite easy to prove that there's no dependence on V parallel for these trapped particles. Like these parallel, in order for a particle to become trapped, it needs very small initial energy, parallel energy, otherwise it will just blast through the region. So all trapped particles become trapped with an initial small e parallel. So the energy of which they get trapped with is the magnetic moment times the magnetic field strength out there. And from that, you can back out that this region has to be flat. Okay. So far we have only considered magnetic forces. Now there may also be electrical forces. And there may in particular be a parallel potential in here. So let's assume that this is, I will clarify what this parallel potential is. But let's assume it's somehow positively charged in here. Then my initial particle going in, they will be accelerated by the magnetic forces, but also by the electric forces. So what it basically amounts to is to stretch this whole distribution function. The trapped part is still independent of V parallel. So that's basically the effect of the electric forces, is to stretch the whole solution. Stretch in V parallel. Yeah, so here you have the trapped passing boundary. So you basically move those in the parallel direction. Out here it stays a Maxwellian, it's Maxwellian here, and in between it's a Maxwellian in the perp direction and flat in the parallel direction. Yeah, so in these limits where the electrons, they move much faster than the field lines are convecting in, this is the adiabatic solution that you find. And it's exact in the limit where the bounce time is infinitely faster than the in convection.
So this is a solution of the collisionless velocity.
Yeah.
For a given magnetic structure configuration.
Yeah, it turns out like it's amazing. It doesn't depend on the structure. It just depends on the local value of the potential and the local B. It's remarkable. Like the structure drops out totally.
Okay.
Just because we use
because you just have two invariants, mu and
we use conserved quantities. Right, so we have a very simple expression for the distribution function, and now I can go back and compare to the wind observations. And so here is our model, and here's the wind. And if I assume there is a potential of about a kilovolt, right, then this is electrons. Yeah. And so the ions wouldn't do this because they're not fast compared to the inflow. You need the fast bouncing. Okay, so just one point about this potential. I think in my paper from 2005, I just called it electrostatic trapping. But this is really a potential that's field aligned. So you have to integrate up the total electric field along the field line, whatever geometrical shape they may have. So it's not a real potential. It's like a solar potential. They basically measure how much energy a particle will have to get out of the region to overcome the forces of the electric field along a given field line. Okay. Like, so there has been some concern about this potential actually develop in a kinetic code, and this is run by Bill Dorton, and you see you have a potential that goes up to about 8 external temperatures here. So basically every single electron in this
So the color here is the potential?
is the potential, and super red is 8 external temperatures. So every thermal electron here in this simulation will be trapped on trajectories like this one.
No, this is
So pretty much, if I go back here, this,
there is a guide field here. So
yeah, it's a nothing
no
moment.
guide field, basically.
Sorry?
I'm just trying to see.
There's a guide for you, yeah, so there you go.
From where? From the center? From where to where? Not the potential, but this integral, the parallel integral is taking from.
Yeah, so
where
you
to-
take a given point here, you integrate along your field line out until the boundary.
Okay.
And it turns out it doesn't matter which way you integrate. The value you get is almost identical, whether you integrate one way or the other.
What do you assume is the boundary?
So the boundary, like you just integrate until you hit the boundary, then you stop integrating. So assuming the potential is 0 at the boundary.
Okay. Why is that?
Yeah, I will get to that, actually. Like, you need one step more. Okay, so it looks like this potential develops self-consistently in the code. And like, why would that happen? So let's look a little bit more at this solution we have found. So what I'm going to do here is I'm going to show the V parallel, V perp space, my solution, and also in 3D velocity space down here. And then I'm going to ramp down the magnetic field. Let me just do it now. So I'm ramping down the field, and you see this trap passing boundary is developing. You have the trap population in between here. So this is like approaching the X-line. Here in 3D, you see the trap passing boundaries as well. And here you have the flat part. And
Where is the picture, the distribution function? Where in space is that considered?
it could be anywhere, anywhere in space where B is exactly 0.5 now of the external B.
Okay. So it doesn't matter. What matters is the local value.
Uh-huh.
The local value of the potential.
Right. Okay, so let me do it again. So now I'm going to spin it, so you can see the. So here I basically have 2 cones with the passing populations here and the trapped in between. And as I ramp down my B, you see the density gone down because we got rid of all the particles that before were up here. So magnetic trapping alone will make your density go down. Because B goes down, B perp goes down, it basically leads to cooling, and that gives you less particle, less density. Now the ions don't do that. They don't lose density due to this mechanism. So you have to pull in electrons from the outside to keep the plasma quasi-neutral. And the only way you can do that is by developing this potential that makes your distribution function more elongated.
So the electric potential adjusts to keep that density.
Uh-huh. So now I'm turning up the potential, and you see this thing becomes longer and longer. And as I do that, when I wrap up my potential, in this case to 4, I get back the density I had before. So if B goes down by 2, then the potential has to go up by more than 4 in order to get back to the same density. Like, so now we have a distribution function that's really elongated. And that has very high parallel temperature and very small perpendicular temperature. So in this case, the anisotropy is about a factor of 8. P parallel over P perp is a factor of 8. Hugely anisotropic. Okay. So now I'm going to go from my analytical model for F to new equations of state. I'm going to apply, normally when you do your expansion by Ginsky kind of thing, then you apply a Maxwellian. But now we apply this solution.
I have one question subtracting this. Your distribution function that you just showed is has no net velocity, right? And yet your magnetic structure has to be consistent with the currents.
Yeah.
Created, so there must be some.
Like I said, this is exact solution in the limit where we parallel, or the thermal speed is much faster than any other speed. But of course, that's not the case. So this is like the first term in an expansion in the drift speed or the thermal speed. So there will be another term that can shift this one sideways one or the other. But it doesn't really, like that shift doesn't matter for the pressure.
Yeah, you've been talking about just the electron so far.
Yeah, the ions I don't care about.
So is the equations of state that you're going to talk about next are also just for electrons?
Only for the electrons. Yeah. Right, so let's see if we can derive some equations of state. I can take moment over this distribution function to calculate the density, and I can get given that my F only depends on B and the potential, I can get an expression for my density as a function of only B and the potential. Turns out this is a very nice function, and you can basically invert it. So you can get the potential as a function of B and N. So if you tell me what B and N is, I can tell you what this parallel potential is. And that could be either integrated from one boundary on the other. That's why it doesn't matter which way you integrate.
So please tell us.
Okay,
So
but actually,
is it really explicit function or is it?
yeah, it's a nice function. Actually, we like to get rid of this potential altogether. So I'm now going to put this back into my expression for F and eliminate my potential altogether. And by doing that, I can express my parallel pressure in terms of N and B. So this is our new equations of state, and they're easy to map numerically. In MATLAB,
Can you show us what they look like?
here they are.
Okay.
So in the limit of low density, high B, there is no trapping, and it's max radian or it's Boltzmann. In the limit of strong trapping, high potential, you recover CGL scaling. So basically what we have here, this is P parallel as a function of N for a number of different values of B. So you see a low B, the parallel pressure shoots up like this N cubed over B squared. By the low density, you recover the linear scaling of a Boltzmann, where there's no trapping. So we now have bridged the gap between Boltzmann and the CGL scaling. Actually, CGL was derived in the limit of no electric fields.
Oh, sorry. So this is the general, the plot corresponding to the general function, and this is just the asymptotic behavior.
This is the asymptotic behavior all the way out here.
Okay.
And here it's the Boltzmann, and you
But
turn
you
it.
can smoothly match.
Yeah. And let me just show the perpendicular part as well. So at the low B, you get less pressure as a function of density, but it works more or less linearly. Right, so yeah, why is this important? Like there's this famous paper by Ademir that showed that reconnection can become fast when you include an electric field balanced by pressure. And in that work, they use scalar pressure, and the pressure goes like N times T. Now the pressure goes like N cubed over B squared, and the effect of the pressure becomes much, much stronger. If you take E parallel, you have to take the gradient or div of P and then dot it with your unit B vector. If I put in my new scaling for the pressure, I can, if I increase my density by a factor of 2, I can support 20 times more electric field with this scaling than you can do in the isotropic case. Okay, right, so let's compare to the simulations. Does this actually work? And we have compared against simulations both by Bill Dorn and Jim Drake. So this is a run by Bill. And here I show mod B contours. So I'm going to consider some lines where B is constant. But that's where I should have one particular scaling with N. All right, first I'll consider a point close to the X line. The color here is the distribution in the PIC code, and the black lines is our model. So they trace out the color contours quite nicely.
What is the guide field?
This is a guide field of 0.5.
0.5.
Uh-huh.
So it's not even a strong guide.
No, you don't need much to magnetize the electrons. It's done at a mass ratio of 400. So along this black line, the magnetic field is 0.85 normalized to the upstream value. And you see that the actual parallel pressure as a function of density, like along these black lines, you have different values of the density, and they match the predicted scaling quite nicely. I can then go and take the white lines where the magnetic field is smaller, and you see here you get another slope, and again, it matches quite nicely with our scaling that we have derived. So it looks like the simulation, that these equations of state apply to the simulation. So really the important part here is the whole thing together is the trapping potential or the acceleration potential. And it turns out you get very similar structure in the potential both in open boundary simulations and in closed boundary simulations. So it doesn't seem to matter what boundaries you have.
What sort of parallel electric field in the simulation?
So they integrate up to 4 times the external temperature. If you took the reconnection electric field and integrated over a box size, I guess you will get much stronger or much bigger. So it's the parallel electric field are typically 1/10 of the in-plane electric fields or the reconnection electric field.
In your derivation of your equation of state, the equal electric field just doesn't matter?
No. Like in the limit where the electrons go so fast, the only work done is by the parallel electric fields. Okay, so now I'm going to see if we can apply these new scaling results to our new equations of state also to anti-parallel reconnection. And like it's not obvious because in anti-parallel reconnection, the magnetic field goes to 0 and the magnetic moment, you cannot expect that to be conserved. So here is a run of an anti-parallel case. You see the pressure anisotropy is building up here. This is P parallel over P perp, and I'll take log 10 of it. So you see this very nice structure. It's almost like 1D, where the parallel pressure over the perp for this run is a factor of 10 higher than, or the parallel pressure is a factor of 10 higher than the perp pressure. And to go along with it, you have this parallel potential that here gets up to like about 10 external electron temperatures. And then in the exhaust, it's like the parallel and perp pressure are identical. So let's look at that for a little bit, one more time. Right, so this is the trajectory of an electron in this kind of run. It bounces in the inflow because it's trapped in these parallel electric fields and also the magnetic field. And then eventually it gets into the exhaust region. In the exhaust, the magnetic field is very weak. So every time it crosses the midplane here, it will pitch angle scatter. So the magnetic moment is not conserved when you go out here, but it's perfectly conserved as you go in. So the equations of state works in all of the inflow, but not in the exhaust. And here you see the parallel over perp pressure again. You get this like amazing 1D structure. And inside here, you have these electron outflow jets that Bill discovered in 2006. Like they live in between here. Okay, so here I take a vertical cut. The blue lines is the parallel and perp pressure as a function of C. As I'm going along here, that's C. And the red is our model. So again, you see our model is like really capture the anisotropy that develops in this run. It's kind of remarkable. Then you get into the middle part where B is small. Our equations of state predicts very, very high parallel and very, very low perp pressure. But the magnetic moment breaks down, so the blue curves start deviating from the red.
What determines the maximum value of your pressure anisotropy?
I'll get to that. We have a scaling law for that. And just to show that we are not just lucky, like here we have this comparison for the entire run, and it works all the way through.
So I mean, you have P parallel, comma, P perp, so what do you actually plot?
Like so the top curve is P parallel, the bottom curve is
Oh, okay.
the blue ones,
I see.
and the red is our model.
Yeah.
Okay, and again, this is log 10, so here you have almost an order of magnitude difference in parallel and perp pressure. Uh-huh. Actually, in this model, we assume that they are 0. We're only concerned with when you rotate your coordinate system to be aligned with B, we only consider these things in that diagonal. The off-diagonal terms are important inside this inner layer, and also in guy field reconnection, they're important within 60E of the X-line. But other than that, I do not think they're important. So if you want to have reconnection with the guy field, you definitely need these off-diagonal terms. But this is anti-parallel now, and I'm going to get into what controls this inner region now. I'm going to do that now. Okay, so I now want to derive, so our model breaks down in the very middle here inside the layer. So now I want to see, can we actually constrain that layer with this model for the anisotropy. So what I have written down here is J cross B minus diff P. It's basically the Ohm's law for the electrons. So this is J cross B minus diff P, and then we have everything else in the rest of the Ohm's law in this gamma term. And we're going to argue that this is tiny compared to J cross B and diff P. And that has to be equal to 0 for momentum balance. So I want to apply this Ohm's law of pressure electron momentum balance just to this layer, across the layer,
Sorry,
to obtain scaling laws for this.
the electric field?
Sorry?
What is the electric
Electric field is all in here.
Oh, sorry.
So I'm going to consider a small fluid element inside this inner layer, and but there's a lot of current in this layer, so the field lines, they bend really sharply. So there's a lot of magnetic tension on this little fluid element. So as you go across this layer, div of this whole thing explodes because of the B unit vectors, they rotate so quickly. So in order for this whole thing to be zero, this term here basically has to be zero, just upstream of this layer. So this bend in the field line, as Jim Drake says, you have to be marginally unstable to an electron fire hose in order to have field lines that bend so sharply. So that's basically what we find is that I can take the b squared xy from here and the p parallel minus p perp, bx, by, and compare them to one another, and you can see they basically balance one another. And the next term is the biggest one we could find in the gamma. So the terms that has to do with the pressure and isotropy, they totally dominate everything else for this layer. So the conditional momentum balance for the layer is that p parallel minus p perp has to be equal to b squared. I now know my equations of state, so I can solve for b in this equation. And I can basically find the upstream value of the magnetic field just upstream of the layer. So now we have a scaling law for this upstream magnetic field, and there is the magnetic field that gets turned into the Hall field when you go further downstream of the layer. And it turns out that this field is sensitive to the upstream electron beta. So it's the electron pressure normalized to the magnetic field pressure upstream of the reconnection region. It seems to matter. I can then plug this back into my equations of state, and I can get scaling laws for the anisotropy, and I can get scaling laws for the potential just upstream of the layer. They look like this.
So this is like just upstream of the layer.
Just upstream of the layer. So according to this theory, at low beta, the Hall field should drop off, and the potential or the anisotropy should explode, and so should the parallel potential. And at least we have 3 points on this curve. I think we have more points now, but the circles here is the periodic boundary simulations by Jim Drake, and the crosses are from Bill Dalton's. Okay. Nice. Remember again, this is the upstream magnetic field. This is basically how much current you have in this inner layer. And it only depends on this upstream beta. So this suggests that the reconnection electric field is not important for what current you get in that inner layer. And so it basically controls the surface current in the layer, this anisotropy. And I think it's kind of counterintuitive to what many people have been thinking about. They think like a fluid element coming in here, and then it gets accelerated, and you get the current. That's the standard way that people think about how to generate currents in the plasma. So Bill's test of whether I was nuts or not was to take his code and modify the Lorentz operator for the y direction. So basically, he just took Ey inside this region and multiplied it by 0. So the electrons will not feel a force from Ey. So now we've done this run where Ey is 0, and the current sheet actually becomes wider. And the current density does go down inside the layer. But when you integrate it up, basically integrate it up to the magnetic field, you see you get exactly the same magnetic field when you just go 4 or 5 dE outside. So the total current in the layer appears to be controlled by the upstream pressure anisotropy.
So what's the dynamical process? In other words, if your P parallel over P perp gets too big, what causes it to relax? Is there a fire hose thing or what?
Like this condition here, if B is too small and it happens over a nice smooth region such that the magnetic moment is conserved, then the equations of state will hold and they would drive really high P parallel. And eventually it will settle in so that you have this balance that Like if there was too low B, you would get higher P parallel, that would drive more current, that would make B higher. So there's a very strong feedback in this equation here. And you see,
But how does it drive more current then? That's what I'm trying to understand.
yes, I'll show you in the next slide again that P parallel actually drives the current in the layer. I'll show how that happens. Like so a little bit less beta, you get a stronger potential, and that will, yeah, it bites its own tail. Okay, we also did a test where we doubled the force on the electrons, just to be sure. And in that case, we get a little bit extra current, but now the layer is a little bit thinner, and again, you can hardly see any difference in the magnetic field. So the total current, again, is totally controlled by this pressure condition. Okay, yeah, so how do we actually get the current in the layer from this anisotropy? Now you should now imagine you're sitting down here, you have a distribution function that has T parallel over T perp maybe 10. So it's like you're injecting beams of zero perpendicular energy but high parallel velocity. If you want to hit the X line, then there's a number of ways you can do it. You can inject a particle that goes straight in, but it turns out this layer can reflect particles very efficiently. So you can also go in there by bouncing once, or maybe you bounce twice, or you can bounce many, many times. So when you look at the distribution function in there, we figured out a way to recreate it using a lasso technique. You get this crazy structure, it's just amazing. Each stripe here are now colored according to the number of reflections. So the particles that come in straight, they give you this striation here.
So which reflections are these? Is that big bounces or
There's reflections inside this inner layer.
inside, across the middle?
Yeah, it's not the big bounces, it's inside the inner layer.
So these are contours of what?
This is isosurfaces of a given phase space density. And we build it up by tracing particle orbits back in time until we reach a point here where we know what F is.
Oh, so you know the history of each
Yeah, we know, exactly. And you see a higher bounces, then you get this peak in the y direction. So basically what happens is that the particle, as they come in here, they do get accelerated a little bit in the y direction by the reconnection electric field. But the main thing that drives the current is that the Vx.bc force on them rotates the velocity of this beam into the y direction. And that's how the current is generated for the most part. And the tips here are pulled out at it looks like two Christmas trees with like pointy tips. And maybe you can see that here. I'm going to rotate it. And so the tips are pulled out by the reconnection electric field. And that's when you have a lot of bounces, then they spend more time in there, and the effect of them is bigger. Okay. So I guess what I'm saying is it's consistent with Jim Drake's point for many years that you can support any electric field at the electron scale, and the electric field is not important for this inner electron diffusion region. Also, of course, people are still interested in what really does balance the reconnection electric field. So what we find is that it is the pxpy, the gradient in the pxpy. If I take my distribution function to the left of the layer of the x-line and compare it to one to the right, you can see it's like this tree has rotated, and that gives you a gradient in p parallel, not in pxpy, that can balance. This is the main effect of turning on the electric field. If I turn off the electric field, as we did, then this is just like a round structure, and when you rotate it, you don't get any effect of in the pxpy gradient.
So there is a pressure non-gyrotropic in the simulations. Does it?
Yeah, so in the layer, this is totally non-gyrotropic at all. Right? This is like as
Now,
far
in
away.
In the case this is our guide field. In the case with the guide field, in your theory, what balance is there?
Probably Hess's theory will apply. We haven't really looked into that, but I just assume Hesse was right.
But we're claiming that low beta, it doesn't work.
Okay, so then it's something else.
About that one.
Okay, so is this applicable to spacecraft observations? Like I looked at some data from cluster in particular. So Li Jianchen looked at this October 1st event from 2001, very famous. I think it was the first big event that cluster saw, so everybody has looked at this. And she created this map. Like the 4 cluster spacecraft apparently moved through this reconnection region in this fashion. She determined if the spacecraft was in the exhaust or in the inflow by looking at the electron anisotropy. So here you see her map of electron distribution function. This is parallel and this is perp. So you see all the way up here you have very high parallel pressure compared to perp pressure. In the exhaust it's more isotropic. So that's how she recreated this map. If you take one particular point in the inflow here, you can see our model works quite well. Here the data points is from the spacecraft and the lines is from our model. And we have log 10 of F versus log 10 of the energy for a number of different angles. So again, you have high parallel pressure compared to perp pressure. So definitely.
Is this a guide field case or a non-guide field?
No guide field.
No guide field.
And then the exhaust is totally isotropic. So here I'm going to show a few distributions as you cross from the exhaust into the inflow. This is a typical exhaust distribution where it's what they call flat top up to 10 kilovolts and then it drops off really rapidly. And it's totally isotropic, so this is how she determined this was in the exhaust. And then here we have one again from the inflow region where the parallel pressure is way higher than the perp pressure. And this is what it looks when you go from one thing to the other.
So there is a solid line? Or
Solid line is parallel, and the other guys is perpendicular. It's nearly parallel, nearly perpendicular.
which one? Which one is theory, which one is observation? The data points are observation.
Like this is my fit with the analytical function to the data points. So you see we can fit it in the inflow region up till we get really close where you have p-cycle scattering. And then in the exhaust, of course, our theory does not apply, where it's isotropic. Okay, so like basically the bend, very sharp bend, is really easy to eyeball when you're just looking at the graph. And that gives you the value of the potential. So by studying this distribution, I can get the actual value for the parallel potential. And this is what I get when I consider cluster 3 that went through like this. And these data points here is basically from those in this figure. So what we find is that in the inflow region, the potential is quite small, and then it goes smoothly up, or at least on a log scale, to the potential seen in the exhaust. In the exhaust, it's up to 10 kilovolts, maybe even more, and in the inflow, it's typically around a kilovolt. And I've done this for all the 4 spacecrafts, and this is what we find. So again, in the exhaust, the potential is really high, if you believe that bend in the distribution corresponds to the potential. So in the exhaust, we find that the potential is about 150 external temperatures, and the inflow it might be up to 50 external temperatures. Let's compare to the simulation. In the simulation, I had 8 external temperatures. Right. So it seems like in these spacecraft observations, the potential is much, much stronger. And this is typical for all the simulations in the literature, I think. So something seems to be off. Also, you see here the potential in the simulation is kind of localized right around the diffusion region, and in the exhaust there's not really much to speak of, whereas it's the opposite for the spacecraft's observations. But if we call this scaling here, at low beta, I should get a very high potential. And the simulations are done, like they agree with the theory, but they're done at a pretty high beta. The cluster beta is about 3 per mil, whereas typically in simulations you apply a beta of maybe 5%.
So where in the tail is this, was the cluster observation?
It's 20 years radii.
How many?
20.
20. So it's pretty low beta. Wow. This must be low plasma coming in, is that what's going on?
Yeah, I think that's, I don't know, that's typical for reconnection events, that you have a lobe distribution coming in. Yeah.
Yeah, yeah.
They were forcing down, but if something were pushing those 2 regions together, would that
It shouldn't matter for our equations.
not for this relatively high power level?
Like our scaling law is obtained just by having momentum balance across the layer. It shouldn't matter if you force it or not. The only thing we require is the magnetic moment being conserved and the bounce time being fast.
So that dependence was very weak, right? It was 1 cube.
Like it goes like this, so it gets pretty steep when you get a small enough band.
The dependence of beta was 1/3 minus 1/3. Well, I don't remember.
It's 1 divided by, I think, square root of beta.
6?
1 divided by the square root.
Oh, the square root.
Uh-huh.
So
Okay.
the batch.
So yeah, I asked Bill to make a simulation with low beta, and he did one, and I wasn't happy. So I asked him to, could you double it, the length of it? And so he did that. Like a week later, it arrived on my hard disk. And I still wasn't happy. So I kept doing it. I think I made him double it 4 times. So this is just a monster simulation now.
Double the box, right?
Double the length of the box 4 times. So this is a monster simulation. I think it's 70 billion particles and 160 di long and a mass ratio of 400. So let's run it here. And now you see this potential building up, and it reaches 40 external temperatures.
This is all 2D, right?
It's all 2D still. And another point is that the potential stays up in the entire exhaust. Everything that's reconnected, the potential stays high. That's opposite from the smaller simulation I showed before. So the potential is substantial. And now here, this is log 10 of the density. So it looks like the potential, in this case, in guide field reconnection, you always see these asymmetric density perturbation. Now in anti-parallel reconnection, it looks like we have the same density perturbations on all 4 separators that supports strong parallel electric fields.
So its potential is assigned to bring in the electrons then?
Yeah, they're bringing them in.
It brings them in.
Uh-huh.
Okay, so this is with guide field?
No guide field here.
And does it bring them in from the outside boundaries?
Yeah, accelerates them in from the.
So are electrons being dragged in from the ends then to fill in this region?
I think the acceleration mostly happens here. You do get some effects at the boundary. Actually, if you run this later in this run, this density perturbation here merges with this density perturbation, and in that case, you get really enormous potentials that I don't believe. But I believe the potential structure at this point in time, and that's why I made him double it so many times, because I wanted this boundary effect to go far away.
Just to get back to that point, I mean, you can make that potential as large as you want if you were to force that simulation.
Well, that's good then. Then you can get a lot of heating. But I think the scaling law for the potential, like, it's given by these equations just across the layer. So I don't think it helps if you force it. It should still be the same. Like
I
you,
wouldn't think it would matter. The potential would. You're saying they would. No.
the potential is not the reconnection rate. It's a parallel potential across the entire field line that develops self-consistently to maintain quasi-neutrality. And it doesn't depend at all on the reconnection rate.
The physics of this is, again, the flux tube comes in and moves it, the central part moves into a region of weak magnetic field that expands.
Uh-huh. And you
fill
need
the
to.
volume, you need to bring in electrons
Yeah.
to the electric field.
Okay, so now I want to discuss if this is important for heating, and let's go back to some observations. Now first, let's compare to a previous simulation. This is the one I showed before.
It directly turns it to parallel pressure, not.
So now we have 40 TE, and before we had 4. And I stepped down my beta by about a factor of 10 to obtain this. The electron temperature was stepped down by a factor of 2. So really, we normalize the potential to the temperature, but we see an increase in a factor of 10 in the potential, but TE has only been decreased by a factor of 2. So it's really the electric fields has increased. Like the decrease in beta is mainly obtained by decreasing the external lobe density. And again, this is how big that simulation was compared to this new one. And you see the structure is now way, way bigger than it was before. Like the potential really lives in a way, way bigger area. Okay, so there's a famous observation by that guy, he used Gyrotail, and he showed that there's very strong kinetic effects in the Hall current. So what is quite often observed is a beam, like a beam-like structure here, going in towards the X-line. And less dense stuff, but hotter, is leaving the X-line region. And here's another case where the beam is again directed towards the x-line and more hot stuff is leaving. So in this representation, you can see the asymmetry. You have, again, you have a cold beam going in, they call it, and a hot beam going out. And like I've read the literature a little bit, and there's a lot of ways to try to explain this using waves and stuff. It doesn't seem convincing to me. So that's one reason why I was so interested in these low beta simulations. I wanted to explain the structure. And now in this simulation, I think that we see this. Like at this point down here, B is directed towards the x-line. And if I look at the distribution function, I see exactly this little beam structure that you have seen with Geotail. So the reason why we see it now is that the potential is so big that you can pull out the structure out of your Maxwellian. The other stuff here is
That means that
that this beam here is coming straight in.
Than the thermal velocity.
Yeah. So it's pulled right out of your initial Maxwellian. So this beam here comes from the boundary and is accelerated in. All the other stuff is coming back from the reconnection x-line. The stuff with minus V parallel definitely comes from there. And this part that has positive V parallel will have come back and then reflected and come back. So the trap passing boundary is sitting right here. And all these particles is coming from the exhaust. They have Pitts angle scattered in the low B, and that's why it's totally isotropic.
So, Jan, is this different from the beams we've seen in the past then, or what?
But this is the past. And this
Well,
is,
I mean, I'm talking about the simulation past. So, I mean, we always see the electrons coming in outside this region here. Is it different, or?
it's the first time I've seen it in build simulation this clear. Like, I'm not,
This is the electron
We
current
always saw
that
electron
creates
beams
the
coming in.
quadrupole magnetic field.
like, I never,
You always had it.
Yeah, we always had it. So
So
I'm
this
trying
is
to
what
see if
creates
you always had the whole field, but I haven't really seen much data or particle data like this from the simulations.
But we always showed these electron beams coming out. And
In
then
which,
that's the
in
Hall
which
current.
fashion do you show the beam? Like in the moments, or in the structure in the distribution function?
Well, we showed the moments, but it's very large.
Yeah, I believe that you get you always
I'm
give the
trying to
beams.
say if there's I'm trying to understand if there's something fundamentally different than what we've seen in the past. Did we miss something? Or that's what I'm asking.
Like I think Taifan and others, they see these beams like hundreds of, or I don't know, 20s of DIs away from the X-line. And I always had the impression that the Hall currents and the beams in the Hall current system in the simulation was like a fluid stuff happening a few DI of the X-line. So this is definitely a kinetic effect. Yeah, and I cannot say.
Because
J,
some of these
J is equal to the curl of B.
you know, keep in mind that when they saw that, it was because of the earlier simulations in which we predicted all that. And they identified that as one of the key signatures of Hall reconnection.
So
So I don't know
I
if you're seeing something fundamentally different as a drive, or I mean, we probably didn't get the drive right, or we didn't explain it. I guess.
like again, if this is the state-of-the-art simulation a year ago, and that simulation does not have that feature I just showed, and there's no agreement, or you don't have that detailed agreement with the spacecraft observation. Like surely you have Hall currents inside this region in this simulation, but I don't think you have it on that length scale.
Do you have a Hall current system in the earlier simulation?
Sure, yeah.
Yeah, you
No,
did.
these are typical size. I mean, that little, what is that, like 20 or 30 ion inertial links in the little box, the mass ratio 400.
But maybe so you just didn't separate the beam from the main distribution, is that?
Well, I mean, along the separations and stuff, if you just look at the fluid moments, clearly there's strong streaming.
Yeah, absolutely.
Well, one
But-
thing that
but you-
distinguishes this is that
But
it's
I
very
think-
low beta initially, right? Unlike beam simulation. And that probably allows you to, if you have very small Maxwellian, having the initial Maxwellian, it probably allows you to separate better the beam from the Maxwellian part in terms of the kind of
Uh-huh.
the distribution function. Maybe that's
J is equal to the curl of B, so I think it's a function of just the density and the magnitude of BZ.
Yeah, Maxwell's equations apply. Like God gave us those; they always apply. Then we make up the rest, right? But like I think kinetic effects are important in how long. If you just take your fluid model and you use true fluid, I think you get a different structure than you get in this simulation. Surely you get Hall fields in any true fluid simulation, but I think people are saying that in a kinetic simulation you get different structure for this region. And if you want really long scale structure, I think if you want to reproduce the spacecraft data, I really think that this is what does it. But it might be that two fluid simulation give you the right reconnection rate and most of what you're interested in. But like this is kind of down in the details now. Okay, so now we have these really strong potentials. Like this is normalized to gamma V actually. So you see gamma V is above 1 here. So this is, in this simulation, like this is really hot stuff. This is relativistic particles. I just don't like to call it that because mc squared is, in terms of, like the temperature is too many mc squared compared to nature. This is above, now the magnetic field is facing the other way, so you see the beam on the other side, and you have this passing boundary again. Okay, so I now think we can explain like thermal features in the distribution function, but how about the superthermal? So I looked at some data. This is a data set again from cluster, and the Gen 10 identified magnetic islands in this event. So we see we are looking at the phase space density of superthermal electrons measured by the rapid instrument and cluster. So this is like all from 120 to 180 kilovolts. It's this line here, and then we go down to about 30 kilovolts. And you see these nice features there. I'm considering 4 time points. 2 of them is inside the islands, and the 2 other time points is outside the islands. This one in particular is in the inflow lobe plasma. So this is what the spectra looks like, F versus energy. So the lobe distribution is down here. So now I'm interested in how much did each energy class get accelerated. And you can figure that out very simply. You just have to see how far do you have to shift this incoming distribution function to match the distribution function inside the islands or inside the exhaust. So if I want to match the one measured at this time, the red time, like it looks like my arrows are constant length. So we've done a more careful analysis where we basically measured this length of the arrows as a function of energy. And you see that in order to explain the heating, you just have to apply a constant shift of your initial distribution function. So this means that all your electrons are being accelerated by a constant amount, and that is what an acceleration potential will do. It's totally flat. So I believe that the superthermal heating, at least for this event, is consistent with acceleration in this kind of potential, and the potential goes up to 50 kilovolt. It's enormous. It sounds a little bit unrealistic, but I know, but that's what the data is telling me. And this was just published in the GL very recently. We also looked at the famous wind event where there's a PIL saying electron acceleration to 300 kilovolts, and this was the evidence that you had this bump in the 300 kilovolt channel. And again, I consider 4 different times, not 5. I have this lobe distribution and 4 times closer to the reconnection event. And I get F versus energy here. And again, we infer a flat energy gain spectra. So also for this event, does the acceleration appear to be consistent with just acceleration in the pure potential? Like maybe a troubling fact is that this was observed over hours. So this will suggest that this potential is really, really big scale. And yeah, I think this potential will have to be way, way bigger than even this biggest simulation that I just showed. Okay, so what is the implication for the sun? Jim showed this nice data set from Sam Kruger of the hot X-rays at kilovolts here. And I agree that if you have an isotropic pressure, it's very hard to support any parallel electric fields. If you have isotropic pressure, then your potential will go like the temperature times log n, and you can never make log n big, so you cannot support any electric field if you have isotropic pressure. On the other hand, if we have our new scaling law, that P parallel goes like n squared, or n cubed over b squared, then the potential will go like n squared over b squared. So now suddenly you can support a lot of parallel energy, a lot of parallel electric field. So what happens is that if you go from the outside to the inside, maybe the density goes up, and this distribution function of the electrons, in order to match the ion density, they have to become really, really long to get these cigar-shaped distribution functions. So if I have been consulting with Bob Lin at Berkeley, and he tells me that you can imagine a factor of 10 density increase as you go across the separator here, and maybe B goes down by a factor of 2, that will mean that this factor here becomes 400. And that could certainly explain the observations. And there's nothing more efficient than parallel electric field for heating a plasma. So this would be extremely efficient energization mechanism. So before reconnection sets in, we would assume everything is isotropic. And then as reconnection sets in, these new equations of state should apply. And they should apply to a region that would be roughly the collision times the alpha in speed. And for this event, it corresponds to a region that's about 1/10 of the flare size.
Isn't the reason for very high, so as we
So the equations of state is not linked to the ion inertial length or any other length scale. It's just
basically near the X point, the field line essentially is along the
like you have a guide field.
direction. So it just becomes very long, and you are in your phi you picking up the integral of the reconnecting field.
Like that's a part of the integral, but this applies not just like you have the total electric field, so most of the heating will be done outside by in-plane electric fields that will make up the main part of the potential.
What is the phi parallel? What determines the phi parallel? Would it be?
So if our equations of state work, you just have to tell me N and B, and I can tell you what it is, integrating along whatever the field line is.
Okay. But now this is just the scale of things, but what about the direction? I mean, would it be that?
Right, so the electric field would be pointing in from both sides.
No, okay, but at the very center, at the very at the
Like you can forget about the X line. There's such a small region that it has no interest. Like it's meters. So
So Jan, so let me take you seriously here and say TE is 100 eV initially, so that gets you to 40 kilovolts.
yeah.
So this is, I think you're getting something which is in the realm of the upper limit of their thermal particle distribution. That's the boundary between their thermal and the energetic tail is about 20 kilovolts.
Yes, I'm not saying this is the only mechanism. I'm just saying that this mechanism has to be there. I don't know if it's the most important or not, but
But still, the order, if you're, and I presume you've taken extreme values to try to get this. So it looks like you're getting things up to their thermal distribution, upper edge of their thermal distribution.
like I could
I mean,
imagine.
that's important, so I'm not saying anything against it, but
I could imagine this number being more than 10. Like this is what Bob said, and it could be 20, and that would give me another factor of 4.
yeah, but I think okay, you're going to have to explain the density increase. Oftentimes, you have a flux of plasma from the
And it comes up here, right?
It comes back up and fills this region.
It fills the region below. I think the field line will already have reconnected at the time that, so you wouldn't be able to backfill the region where they
So
see the.
that's the way you're going to get these types of density increases, because otherwise you have to ask.
Like again, when we have reconnection in the magnetotail, you go from the lobe to the sheet, and the density goes way up even during reconnection. So I.
Okay,
So that's
I mean,
the statement that the density can increase by a factor of 10. What does this refer to? Does it refer to the density in the reconnection layer?
When you go
or
from
is
the,
it post-reconnected?
it's like when you go from here to there, I need a factor of 10.
From where to where?
From the externally,
How do they know that?
like so, Sam Kroger says that here the density is 2 10 to the 9, and out here is like
You're saying
1
that
10 to the
this
9
is
plus
the
minus.
result of chromospheric evaporation.
Yeah, no, that wouldn't work. No.
not in the Crocker case, but I don't see how you get a factor of 10 if you don't invoke thermospheric or chromospheric evaporation.
Yeah, I don't know about that. So maybe it's factor of 2, and it will still be substantial heating, but maybe it's not what generates the X-rays.
And is the guide field suppressed?
The guide field is good because that makes our equations of.
The compression. They wouldn't be able to compress the plasma.
Yeah, like I would trust the observations more than anything else, but the density increases. And this is the value Bob gave me, and I believe, but I don't know if it's really well constrained.
I think they've estimated the magnetic field strength, but it's probably by the radio emission or something like that.
Like so
So I don't think they know any directions. They can't measure the magnetic field.
Sure.
I have an email from Sam that says that the density here is 2 10 to the 9, here it's 1 10 to the 9 plus minus an order of magnitude. So I guess they basically don't know what that ratio is.
Yeah, the ion balance,
Guess I'll let Bill solve that in his code.
very strong part of it. Really, it should be considered by
I'm sorry, I didn't hear.
We effectively moved into the questions period, right?
Oh, wait, now we're going beyond.
Oh, let me just go through the conclusion. So we have a model for F, a new model for P parallel and P perp, and they apply to the inflow. They apply everywhere in guide field reconnection. They apply to the inflow region anti-parallel reconnection. They set the structure of this inner layer, the outflow jets. And in spacecraft observation, you observe very strong phi, and in our simulation or in our model, that scales with, like phi should become big and large phi parallel, and it should influence the whole current system. And I think phi parallel is important for electron heating in the tail, and maybe also on the sun. I know the last point is pushing it, but